We'll begin our discussion under the topic chemical bonding within the context of chemistry. So under this topic, we're going to look at the different kinds of chemical bonds that we have. So things like the ionic bonds, we'll go into details, how basically they get to form, looking at the effect of the lattice energy and also the electron configuration. From there, we'll get to look at the covalent bonding, look at the different kinds of covalent bonds that we have, realize that we've got polar covalent, non-polar covalent bonds, and then we'll begin looking at the Lewis structures of all these different compounds. For example, carbon dioxide, we know that this Lewis structure is linear in that we have oxygen like that, okay? So we'll begin accounting for why water is different as well, and other structures. We'll see that despite them having the same number of atoms, they basically get to be arranged in a different way. So that is under molecular geometry and electron geometry, looking at the effect of the existence of lone pair electrons on the central atom. And of course, we'll look at what makes us choose the central atom. What do we basically get to look at? So look at the effect of electronegativity on choosing the central atom. We'll look at the bond polarity, we'll look at formal charges, we'll get to look at the resonance structures, okay? In addition to all that, we'll basically get to look at the exceptions to the octet rule, the bond enthalpy, and also the length of bonds. So this is going to be a very interesting topic. I encourage you to make sure you watch all the videos for you to get a full understanding to the topic. Okay, so before we get to end this video, we'd have to understand basically what chemical bonding is. What exactly is chemical bonding? How would you define it formally? So basically, we can just define this term, chemical bonding, just to be the formation of a bond between two or more atoms or molecules to give rise to a compound. So a compound is a result of bonds between two or more atoms, of course, of different elements in most of the cases. Okay, so that's exactly what chemical bonding is. So realize we'll look at chemical bonding, we'll basically get to understand whether it's an endothermic. When we're looking at the bond formation, is it an endothermic or exothermic reaction? All that will be discussed as we get to proceed. Okay, so Lewis theory will be very interesting as we get to look at the Lewis structures. Okay, let's now begin to look at the different kinds of bonding that we do have. So I'll start with the ionic bonding. So what exactly is ionic bonding? So ionic bonding is basically an electrostatic attraction that occurs between ions. Okay, so that's very simple for us to basically understand. In that, we know that we're looking at ions because it's ionic, okay? So we know what an ion is. So an ion is basically an atom that has lost or gained electrons. Okay, so for example, if you look at sodium plus and then chloride minus, this is a cation which has lost an electron by virtue of it having a positive charge. A chloride has gained an extra electron. So these are ions. So a kind of bonding that exists between such ions is what we are calling ionic bonding. Okay. So we've built an argument to say ionic bonding basically gets to form between ions. So there's an electrostatic attraction between cations and the anions. That's our first thing that we've started with. So basically, in an equation, we can write something like this. So we know that sodium has got one electron in its outermost shell. And then it's getting to react with chlorine. We know chlorine is in group 7. So it equally has got 7 electrons in its outermost what? Shell. Okay, so we understand that atoms have got desire to attain stability by observing the octet rule. Okay, that's basically what we know. So we understand that in this case, this chlorine is having 7 electrons. So it is in need of an extra electron for it to become what? To become stable. So in terms of showing what's basically going to happen is this. We know that sodium has got 11 electrons in its neutral state. In that, if you try to write the electronic configuration, we've got 2 to 8 and then 1. So if you add these, will give you 11. So it's better for it to lose. It's easier for it to lose that single electron to remain with 8 in its outermost shell than gain the 7. So that's why metals tend to lose, and then it is easier for chlorine to gain 1 than lose all the 7. Okay, so expect that our result is going to be sodium will lose its electron, and then it will just remain like that. With a positive charge, of course, we can add a positive charge to indicate that it was what? It had lost an electron. And then we have chlorine basically with its 7 electrons, now gaining an extra from what? From the sodium atom. That's the result. So this can be in brackets, and then you can put the minus charge there. So it's negative charge, implying that it has gained an electron from another atom. Okay. That is in an equation form illustrating what basically happens under ionic bonding. So we can also show this diagrammatically, okay, which is very much easy as well. So if you look at sodium, I'll just show the outermost shells for the sake of time. So we understand that is sodium, that is chlorine. So this has got, I'll use X's for chlorine. So it has got 7 electrons, okay. And then for chlorine, I'll use a dot. So it only adds the single electron there. Now what basically gets to happen is I'll show what basically happens on the bottom. So we expect that the sodium now will lose, this will go away. So what is going to remain as the outermost shell? Remember we said this electron configuration was 2, 8, and 1. So it's losing the 1 which is in the outermost shell. So what will remain as the outermost shell is the inner energy level with how many electrons? With 8 electrons. So this makes sense if you did electron configuration from atomic structure. So what is our sodium after? So we can put it also in brackets, and then I'll put a charge of a positive to illustrate that we had lost an electron, and then I'll draw another bracket, and then I'll put chlorine. So chlorine will remain as it is. I'll show the crosses there, which were 7. Now in addition to that, it has gained what? It has gained a dot from sodium. So that's what has formed that. So it has now gained the negative charge. So these two will be a single compound because they are being attracted to each other due to electrostatic attractions, due to their difference in what? In charges. So this is exactly what ionic bonding is. So if you are to break an ionic bond between sodium chloride, there's a lot of energy required to do that. So that energy that is required to break an ionic bond into its ions is what we call lattice energy. Okay, so you look at that more in details as we get to discuss thermochemistry later on in the course. Covalent bonding is the other kind of bonding that we are now talking about. Okay, so unlike ionic bonding, which involves transfer of electrons from the cation to the anion, covalent bonding involves sharing of electrons. So that is exactly what covalent bonding. Covalent bonding forms between nanometals involving the share of electrons. An example is H2. So hydrogen, basically, hydrogen has got a single electron, another hydrogen has got a single electron. So these come together and form a bond. So that is an example of a covalent bond. It is involving sharing of electrons. So diagrammatically, we know that what is basically going to happen is this. So we can show an overlap between the two. And then we can put the electrons in between to show that we had 2 electrons of the 2 hydrogen atoms. Okay, that's exactly what covalent bonding is in simple terms. So we've seen that hydrogen basically involved an equal sharing of electrons. So we can classify covalent bonding into different types: polar covalent bond and non-polar covalent bonding. So what exactly are these? What's polar? What's non-polar covalent bonding? Okay, so in a case where we have equal sharing of electrons, in most of the cases it involves the same type of an element. For example, hydrogen 2, fluorine 2, oxygen 2. All those examples of non-polar covalent bonds. Okay, so equal sharing of electrons is non-polar covalent bonding. Now on the other hand, polar covalent bonding basically involves high difference in electronegativity between the elements involved in the bond formation. For example, hydrogen fluoride, despite knowing the fact that they've equally contributed as a single electron in the bond, so chemically we basically understand that electrons are going to spend more time around the fluorine atom than on the hydrogen atom, due to the fact that fluorine is highly electronegative, so making hydrogen to be partially positive in that bond. Of course, this is what even brings birth to things like hydrogen bonding. Okay, so polar covalent bonding. Okay, so in the next video I'll basically get to explain in terms of, if I give you the values, how do you tell which difference will bring birth to polar covalent bonding. Okay, so it's not always a case that if you've got different atoms or different elements, then you expect that it's polar. No. So look at other examples of non-polar covalent bonds that involve 2 different elements. Okay, so basically this is an introduction to what we need to expect under covalent bonding. All right, so we'll continue looking at polar covalent bonds. So from the previous video, we've built an argument to say our foundation is based on the fact that polar covalent bonds involves non-equal sharing of electrons, where we said for equal sharing of electrons, that is called non-polar covalent bond. So I gave you good examples of non-polar covalent bonds where we have equal sharing of electrons. So the very first example you can notice, any 2 elements or any 2 atoms of the same element, that is, for example, oxygen, nitrogen, provided they are of the same element, all these are non-polar since they have got the same electronegativity, so they share electrons equally. Okay, now I did also state that they are not the only examples. Okay, I said not all different elements forming a chemical bond are polar. Some of them are also non-polar. So some of the examples we can talk about, for example, if you look at carbon and hydrogen. Carbon and a hydrogen bond, this bond is also non-polar. There's equal sharing of electrons between carbon and hydrogen. Okay, we can also look at bromine and chlorine, oxygen and chlorine. All these are non-polar. They share electrons equally. Okay, so I'm now going to introduce you to an aspect of you looking at the difference in terms of electronegativity as a way of classifying bonds as polar and non-polar. So for non-polar, provided the difference in electronegativity is less than 0.4, so 0.4 or less is basically a non-polar. Okay, So you understand with that, if you're looking at if you're looking of atoms of the same element, the difference is a zero. So that classifies them as non-polar. Okay. Now, if you try to look at the carbon has got an electronegativity value of 2.5. And then if you try to look at the hydrogen that I've put there, hydrogen has got an electronegativity value of 2.1. Now let's try to find the difference. So we realize that the difference here is 0.4. So which also classifies it under non-polar. So the difference in electronegativity helps you also classify bonds to be polar or non-polar covariant bonds. Now, giving more examples under polar covariant, we can look at examples with chlorine and fluorine. That is a non-equal sharing of electrons. So again, I did emphasize to say electrons may contribute equal number of electrons, but the aspect of polar implies electrons get to spend more time on one side of a bond than the other side. Okay, so that is an example. We can also look at the OH, the hydroxide, which is a very common kind of a bond. It's also polar, nitrogen, hydrogen, carbon, chlorine. Okay, so we can do a test between carbon and fluorine there. So carbon, I did mention to say it has got a value of 2.5. Now fluorine has got a value of 4. So if you try to find the difference, I'll find the difference is 2.5, right? Sorry, the difference is 1.5. So 1.5 is obviously greater than 0.4. So any value that is between greater than 0.4, that is from 0.4 all the way up to 1.8, that difference classifies polar covariant bonds. Okay. So of course, any difference other than 1.8 would imply that we're looking at now a metal and a non-metal. And of course, from our observation, we've noticed that if I try to give you the values of the non-metals, sorry, the metals now. If I look, like, for example, beryllium has got a value of 1.5, lithium has got a value of 1. So you're saying that even as you get to go down the periodic table, sodium basically gets to have 0.9 and whatnot. So, of course, we understand electronegativity is the ability of atoms to attract electrons to itself. Okay? So we are saying that these nanometals have got a higher ability. They attract electrons more. In fact, we understand in the video we are going to talk about the periodic table trends. We understand that from the left to the right of the periodic table, we basically, the electronegativity gets to increase, and of course up a period, that is right of a period, and then up the periodic table, that is within a group, electronegativity gets to increase. So the difference, we basically get to have a difference other than 1.8 as we begin to compare metals and non-metals, which now gives rise to the ionic bonding. Okay, so now we understand what a polar covariant bond is, and also from the values you know now how to determine which one is polar and also non-polar by looking at the values of the electronegativity. We've built a foundation to say electrons are not always shared equally between the atoms. Okay, so there are cases, of course, where we say it is a polar covariant bond where there is non-equal sharing of electrons, and then the case where there are equal electrons shared, equal sharing of electrons, that is called non-polar. So bond polarity basically is just the measure of how equally or unequally the electrons in a covariant bond are shared. Okay, so we are measuring how equally or unequally the electrons in a covariant bond are measured. So of course in non-polar, as I've mentioned, there's an equal sharing of electrons. And then of course in a polar covariant bond, there is an equal sharing of electrons, unequal. So it's not equal sharing of electrons. Okay, that's basically what bond polarity is concerned about. We've already talked about polar covariant bonds, where we've seen that there's an equal sharing of electrons. So we saw that, for example, in the hydrogen chloride, okay, we saw that chlorine is actually more electronegative as compared to the hydrogen, the difference is greater than 1.8. Sorry, difference is greater than 0.4, but less than 1.8. So that makes that to be polar covalent bonds. So in that case, we expect that electrons will spend more time near the chlorine atom since it's higher in terms of electronegativity compared to the hydrogen atom. So that difference creates what we call partial charges. So we expect that hydrogen is going to be partially positive, and then chlorine is going to be partially negative because the electrons will be spending more time on the chlorine part. So due to that effect, there's an arise of what we are now calling a dipole moment. Okay, so while there's a separation of a charge, we expect that there should be an existence of a dipole moment. Okay, so a dipole moment is basically a measure of the polarity of a chemical bond between two atoms in a molecule. So the measure of polarity of a chemical bond between two atoms, that's basically what we're calling a dipole moment. So they're not going to be more interested in defining the dipole moment. They're going to be asking you in most of the cases, does the dipole moment exist? Okay, so we'll understand later even how we get to perform calculations in regards to this. So I can give you an example. A dipole moment can be drawn for this same compound that we have. So we can draw it this way. So we've seen that electrons move from the partially positive one towards the partially negative one. So a dipole moment has got magnitude as well as direction, as we can see from what I've put there. Okay. So a few things that you would have to note about a dipole moment. The first thing is there may be some cases where you have a dipole moment between two atoms in a compound, but then when it comes to the entire compound, you find that it has got a zero as a net dipole moment. Okay, so look at such an example of a compound. But just before we get to look at such an example, let me basically get to give you this example. So we have beryllium fluoride. So this is the expected Lewis structure. Of course, to understand how we get to draw Lewis structures in the next video, because it will be essential in cases where they ask you, they just give you the formula, because we know that for beryllium fluoride, we expect the formula is BeF2. That is beryllium fluoride. So if we put Be there, and then we put two fluorine atoms, this is basically the Lewis structure of beryllium fluoride. So of course, there's a single bond existence. Okay. So in this case, beryllium is a metal. Okay, so we understand this is ionic bonding and whatnot. But despite all that, beryllium being a metal, what do we expect? So we expect that it's of course less electronegative as compared to fluorine. Actually, fluorine is the most electronegative element. So what it's going to be is the moment will be away from the positive one towards the negative one, which is fluorine in this case. So we have a dipole moment existing between the fluorine atom on the left and also the right with the beryllium in between. So these are the two dipole moments that we have. Okay. Now, the fact that we've got fluorine on both ends, it implies the magnitude of these two are the same. Now, one is going on the positive side, one is going on the negative side. So therefore, if you are asked to determine the net, does this beryllium fluoride itself as a full compound, does it have a dipole? So it has got no dipole. Okay. The net dipole is a zero due to the fact that these are cancelling out. Okay, so that is a bit different from when you try to look at water. So water is not linear. Okay, water is not linear. So if you look at it, this is the way it is. It forms an angle of 104.5 between the two bonds connecting the oxygen to the two hydrogen atoms. Of course, we know the formula of water is H2O. So the angle there formed is 104.5. So in this case, we've got two lone pair of electrons on the oxygen atom. So in this case, oxygen is the most electronegative element. So the hydrogens will be partially positive, implying that the electrons in the bonds will be spending more time on the oxygen part. So oxygen will end up remaining what? Partially negative with two partial charges, that is. Okay. So how is it going to be? Where do we expect the dipole moment to face? We said that it moves from the positive part going to the negative part, right? So if we get to draw them towards the oxygen atom, of course it's parallel to the bonds. Okay. So now my question is, if you look at what we've drawn there, are they cancelling out or they are not? So they are not. So in this case, you have this part, and then you also have this part. So that being an hypotenuse, you can actually even get to draw that is movement here and movement there, movement there, movement here. So they are going up. So that indicates that water is polar. So you can tell by looking at the moments, the dipole moment. So in this case, water is polar. These moments are not cancelling out. So from the previous example, beryllium fluoride, we can say it is non-polar due to the fact of cancelling out of the dipoles. That is, so water is polar due to that fact. Okay. Now, one thing that we'd have to note about the dipole moment is basically the calculation. So the dipole moment comes with a formula. So of course I've made a statement to say the dipole moment helps us determine the polarity of a covalent bond, to determine whether a compound is polar or non-polar, looking at the net dipole. Okay. So what is the formula for determining the dipole moment of a compound, or that is existing between two atoms, that is? So a dipole moment, denoted as mu, is basically equal to the product of the charge multiplied by the distance existing between the two atoms, denoted as r. Okay, so that is basically the formula that you basically get to work with. Okay, Lewis theory of bonding. What basically are fundamental ideas behind it? So number one, valence electrons play a fundamental role in bonding. So when you're dealing with bonding, valence electrons are very important. Okay. Number two, you can take down the notes. The second point is that sometimes we've got transfer of electrons to form covalent bonds. So transfer of electrons to form bonds. So of course that is just the ionic bonding. So we've talked about valence electrons being necessary or very necessary in terms of bonding. Number three, electrons are shared to form covalent bonds. So there's an aspect of sharing of the electrons. Now remember that the first foundation point is valence electrons are the ones that are involved, that can be transferred, and then as well as shared. Now, number four, Lewis theory tells us electrons are transferred such that atom acquires a stable electron configuration. So electrons are transferred such that each atom acquire a stable electron configuration. So after everything has happened, when electrons are transferred, each atom, I'll summarize that, each atom must acquire what? Must acquire a stable electron configuration. So what's stable electron configuration? So all that was discussed under atomic structure. So most of the atoms want to have a maximum of 8 electrons in its outermost shell. Okay. Now, of course, later on, we're going to look at some exceptions to the octet rule. Those ones that want to be stable without even having 8, but a different number, or even less. Okay? So that is exactly what we're going to talk about. So, although the 8 refers to the noble gas electron configuration, which implies the noble gases are stable because they all have 8 electrons in the outermost shell. Okay? So from here, we're now going to look at a Lewis structure in the next video, okay, which is a combination of Lewis symbols that represents the transfer or sharing of electrons between the atoms involved in the formation of a bond. Alright, so we begin our discussion under Lewis structures. So Lewis structures basically are structures that can show the distribution of electrons in a bond and also the lone pair electrons. So that is, for example, if you have hydrogen fluoride, you basically get to show a bond that forms there, and then of course show the lone pair electrons. That's what a Lewis structure is. So that's the simplest Lewis structure we can have. Now, as we begin to progress, we'll be able to look at compounds that get to have more than 3 atoms, like this one. And we actually even get to be more advanced and look at PCl3, all those structures that are very complex. They basically get to give us an idea of how we get to look at Lewis structures. Okay, so beginning with the simplest ones that contain hydrogen. So hydrogen, we all understand that hydrogen is the first element on the periodic table. It has got a single electron. So hydrogen doesn't have to, it's not supposed to meet the octet rule. Okay, we know that the octet rule requires that for an atom to be stable, it's supposed to have 8 electrons in the outermost shell. But that doesn't apply to hydrogen, helium, and lithium. Okay, we'll see later on that even beryllium and boron don't have to attain octet. We'll also begin to advance later and look at some that exceed the octet later on. Okay, but for now in this video we're going to be very basic and look at build the foundation for our Lewis structures. Okay, so the way it is when you're coming up with a Lewis structure that is complex with at least 3 atoms, there's an aspect of choosing the central atom. So when it comes to choosing the central atom, that is the atom that is going to be at the center, joined to the others. In this case, it's obvious it's going to be nitrogen. It's very simple to tell. Okay, so the idea is the central atom should be the least electronegative element. We understand that if we're looking at a periodic table, electronegativity gets to increase from left to right. That means non-metals are actually more electronegative. And then as we go up a group as well, we notice that fluorine is actually the most electronegative element. So electronegativity increases up a group and from left to right. So metals are more electronegative than metals. So with an exception of hydrogen, hydrogen can never be a central atom. Why? Because hydrogen forms a maximum of a single bond. Okay, so hydrogen can never form 2 bonds like this. No. So because the main idea is what we're trying to look at is whenever we are forming a bond, at least under covalent bonding, that is, okay, all the electrons are supposed to be contributed by parties involved, that is the atoms involved. So if you look at hydrogen fluoride, for example, you understand that there's an electron from hydrogen and an electron from fluorine. So in such a case, stability is attained in that fluorine will assume both electrons part of a bond to be part of itself. So in addition to its 7 electrons that it had, there will be an addition of an electron being shared from hydrogen. So the same applies to hydrogen. Hydrogen will assume the entire bond is part of itself, also attaining its stable state. Okay. So we've already seen that hydrogen forms the maximum of a single bond. So it's very easy to basically get to draw hydrogen containing compounds only. So I'll add NH3. So the way it is the number of bonds that are going to be formed around the central atom are supposed to reduce the valence electrons. So I'll start with nitrogen, which is a central atom. The fact that we only have nitrogen and hydrogen, so hydrogen can never be a central atom because it forms a maximum of a single bond. So in this case, it's very direct. We know that hydrogen forms a maximum of what? Of a single bond. So therefore, we've got 3 hydrogen atoms in this case, which I've shown there. Okay, with 3 bonds. So I'll put the hydrogens there. Now, if you look at nitrogen is in group 5. So in group 5, we have a maximum of 5 valence electrons. So out of the 5 valence electrons, nitrogen has used 1 to form a bond with hydrogen, 1 there. So it has used 3, remaining with how many? 2. So the 2 are the ones we are going to refer to as the lone pair electrons. Okay, that's our beginning. It's very easy when you're dealing with hydrogen. So we can also look at another example. We can look at water. So as well, it's very obvious that oxygen is going to be a central atom. Oxygen or hydrogen is never a central atom. So oxygen is in group what? Group 6 of our periodic table. So it has got 6 valence electrons. Okay. So out of the 6, we are going to use how many? 2 to form bonds with the hydrogen atoms. So it's the remaining out of 6 will remain with 4. So the 4 will be like that. So VSEPR theory, as we'll look at it a bit, if you can check out the other video about VSEPR theory. So VSEPR theory tells us that there are repulsions between the lone pair electrons as well as with the bonds. So that will make us to have bonds that are going to be downwards due to the repulsions by the lone pair electrons. So this is where we're going to have our hydrogen atoms. Okay. So it's an angle of 104.3, very unique. So that is the way water comes out. And then for the sake of practice, you can try out CH4. So CH4 is very simple and straightforward. So feel free to pause the video and try that one out. So if you have CH4 is basically having carbon as the only non-hydrogen atom, so it will be the central atom. Now this carbon has got 4 electrons in its outermost shell. It's coming from group 4. Now we also have 4 hydrogen atoms, so it's obvious that all the 4 are going to form bonds. So we can draw 4 bonds around it. So notice that I'm arranging the bonds in a way that they are more away from each other. They're trying to avoid being closer to each other. Okay. So why have I drawn like this? In this case, we don't have any lone pair electrons. So it will just be the bonds pairing with each other when it comes to this. Okay. So basically, what we need to understand is this is the basic introduction to Lewis structures. In the next video, we get to advance and look at complex Lewis structures, where there is need for us to determine the number of valence electrons. Of course, we've already agreed to say we make the least electronegative element to be the central atom. Okay, so we'll build it up from there and see the way we get to advance. We'll begin looking at advanced Lewis structures. So I've got a few that we're going to look at to help us understand. So of course, with 2 examples of the ones that don't attain octet. Okay, so this is also unique. This is unique in that it doesn't apply to, you see what basically gets to happen in terms of sharing of electrons. So of course, when it comes to Lewis structure, Lewis theory tells us the valence electrons are very necessary. Okay. Carbon has got 4 valence electrons. Oxygen has got 6. So we know that the valence electron matches up with the group number. And carbon is from group 4. Oxygen is from group 6. Okay. So I've got a trick that I basically work with when it comes to all this. Okay. So first thing is you'd want to add the number of electrons And of course, this only applies to even number of electrons, as you would see later. Some that basically get to avoid number of electrons. So the total number of valence electrons in this case is equal to 4 plus 6, which is equal to a 10. Now, assume that these two undertain stability individually. That would mean that each having 8 electrons, so it is 8 by 2. So the required number of electrons to attain stability individually would be 16. So we use this trick to determine the number of bonds to form. So 16 minus 10 is 6. So there's a shortage of 6 valence electrons. Okay? In other terms, you can also determine that by just saying, okay, carbon needs 4. Oxygen needs 2 to make it 8 for each. So that gives you total 6 required valence electrons. So divide that by 2. It will give you the number of bonds. So the bonds basically get to replace the shortage, to cover up for the shortage electrons. Okay, so we have 3 bonds to form between carbon and oxygen. Okay, so now that we've determined the number of bonds to form, we know the valence electrons, we can draw. So we have our carbon and our oxygen. How many bonds? 3 bonds. 1, 2, 3. Okay, so I was saying this is a special case because under normal circumstances, we expect that each atom involved is supposed to contribute equivalent to the number of bonds. Now, in this case, carbon basically gets to only contribute 2. The reason is simple. The main goal of bonding is to make sure that the atoms are balanced. Okay, so we have 2 electrons on each side. Why am I putting 2? It's because the bonds that we have are 3 bonds, which are representing 6 electrons. So if you look at each atom, carbon has got 8, 6 from the 3 bonds, and 2 on its own. Equally, if you try to look at the oxygen as well, it's the same concept there. Okay, so understand how this is different from the others as we proceed. We can now go to the other one, which is hydrogen cyanide. This is also an interesting one. Okay, so we'll try to see if it works as well. Try to see if the formula is going to work. We've got 2. So oxygen has got a single valence electron, carbon has got 4, nitrogen has got 5. In this case, we know hydrogen can never be the central atom. So compare hydrogen and carbon. Which one is more electronegative? Which one is lower in terms of electronegativity? So electronegativity increases from left to right. So we know that this is the way we're going to move. So obviously, carbon group 4, nitrogen group 5. So we're moving from left to right. So obviously we know that nitrogen is higher in electronegativity. So carbon is lower. So carbon in this case will be the central atom with hydrogen on the left. So there's no actually rule where it's supposed to be. It can be on any side. But I've just decided to put hydrogen on the left. Okay. So try to determine the number of required electrons. So hydrogen requires how many? So hydrogen basically gets to require a single electron. Since it's having a single electron, carbon will require 4. Nitrogen will require, since it's 5, it will require 3. So if you look at 3 plus 4 plus 1, that gives us a total of how many electrons? 8 electrons, right? So 8 divided by 2. The answer that you're going to get will be what? Will be 4. So expect that we need to have formation of 4 bonds in this case. Now, the funny part is we already know that hydrogen forms the maximum of a single bond. So expect the remaining 3 to be part of the other side. Now, how true is that? So we know that in all normal compounds, we expect that carbon, so every central atom or any atom is supposed to contribute valence electrons corresponding to the number of bonds it has taken part, unlike carbon monoxide. So here we've got a single electron, by the central atom. So we have 4. So they are all used up. So there will be no lone pair electrons on the central atom. For nitrogen had 5 valence electrons. It has used 3 in the bond. So remaining with how many? 2. So I'll put the 2 on the right there. And then for hydrogen only had the single electron, so it has already taken part in the bond formation. So this is the Lewis structure for hydrogen cyanide. Excuse me. Okay, now let's look at O3. Oxygen trioxide. Is it ozone? I don't know how it's called. Anyway, we'll look at it. So O3, which is ozone, is something that is very interesting as well, in that we are looking at a single. So before we even look at that, I can try to gather oxygen, which is O2. So oxygen is O2. So we know that oxygen itself is is in group 6. So obviously we can't talk about 2 oxygen. It's just single one. So each will need 2 to make it 8. So each will need 2 electrons. So 2 plus 2, we need a total number of 4 electrons. So those 4 electrons can be covered up by bonds by dividing by 2, since each bond takes 2 electrons. So 2 bonds will form. So this explains why oxygen is like this. So it exists diatomically with a double bond in between. So of course, each oxygen had 6 valence electrons. So 2 have taken part in the bond formation on each part. So remaining with a number of how many? 4. So if you try to look at one side, 4 on the bond, 4 as lone pairs. So that is already attained stability. Okay. So applying the same concept to ozone, how basically do we get to look at it? So look at O3. How is it going to be? So each has got 6 valence electrons. So each will need 2 by 3. The total number of required electrons will be 6 valence electrons. So there's need of 6 valence electrons to cover up for the shortage. So we'll divide the 6 by 2. So the total number of bonds we expect are 3 bonds. So in that we have the same atom, same atoms, same element. So all the atoms are oxygen. So what are we supposed to do? Any of them can be the central atom. So 1, 2, and 3. So we've seen that there's need to form 3 bonds. So obviously it can be anywhere. There's nothing like deciding, since we've got identical atoms. So I can just put 1 there and then I can put 2 there. We can now balance the valence electrons. On the central atom, our oxygen had 6 valence electrons. So it has used 1, 2, and 3. How many are remaining? How many are remaining for it to go back to its normal state? So we expect that we have 1, 2, and 3. So if you subtract from the 6, you expect to remain with how many? With 3. But I'll put 2. We'll understand why later. We'll go to the left. I can start with the right hand side. How many electrons do we expect? So we've used 2 already in the bond. So I'll put the remaining 4. And then I can go on the leftmost. How many electrons have we used? Only 1 has been used. So how many do you expect to have? So remember that these are 2 electrons. So we need to make sure it attains stability as well. So how many are we going to put? So put 1, 2. So ask yourself a question. How come we've put the 6? All the 6 electrons have been put there. The reason is simple. We want to attain stability. So implying that this bond that is coming from oxygen, this single bond, all the electrons are coming from it, from the central atom. So that's also a unique part. It's a unique compound or unique Lewis structure. So these are the 6 electrons of the central atom. this bond is fully donated by the central atom. Okay? This oxygen is basically having all its valence electrons around it as lone pairs. So we can say this oxygen is actually negative because it has gained an electron, and then the central one is positive. So those ones are what we call formal charges. Okay, so you understand later on how we basically get to calculate formal charges. Okay, we're now somewhere also interesting. We have PCl3. How do we get to look at this one? So understand which groups they're coming from. Phosphorus is coming from group 5, chlorine is coming from group 7. So how many electrons do they need each? Phosphorus needs 3 electrons. Chlorine needs how many? Chlorine needs a single electron each. How many are they? There are 3. So we'll be in need of 3 electrons. So we get to add 3. 3 plus 3. So we have a shortage of 6 electrons. 6 valence electrons are missing. So we can substitute those ones by the number of bonds. We can divide by 2, knowing that each bond is made up of how many electrons? 2 electrons. So we basically get to have a total of 3 bonds are what we're going to have. So we have PCl3. So which one is going to be a central atom? So obviously we know that phosphorus is less electronegative as compared to chlorine, in that chlorine is towards the right. Okay, so therefore phosphorus will be the central atom, and then we'll have chlorine in the sides. How many bonds? 3 bonds. So we've got 3 bonds. So we will just share one equally. Okay, now phosphorus had 5 electrons. It has used 3 in forming bonds. How many are remaining? 2. So it will be on the central part. So I deliberately had placed the bonds like that because I knew there was 2 electrons coming to form a lone pair of electrons on the central atom. Now, look at the chlorine atoms. They have a single bond. So they've all donated a single electron in the bond. So they are remaining with their 6 valence electron each. Since they had 7, only one of their electrons has taken part in the bond formation with the central atom. So that is the Lewis structure of PCl3. Very simple and straightforward. So this is the foundation, and it applies to all even number Lewis structures, except the ones that are going to talk about later on with odd number electrons, and the ones that exceed octet. Okay, so if you try to count the number of valence electrons, we had 5 plus 3 times 7, since we've got 7 each chlorine atom. 7 by 3 is 21 plus 5 is 26. You can count. You'll see that it's going to add up. So you've got 6 plus 6 plus 6, 18. How many are on the central atom? Or the bonds, sorry, the bonds each has got 2, 2, 2. So 18 plus 6, 24. Plus these, 26. So they're already adding up. That's the way Lewis structure is supposed to be. It's supposed to use electrons available, and of course attain stability. So they all have got 8 around them. We are now on the ones with exceptions, the ones that don't reach octet. Beryllium chloride is the first one. So this is a unique part. I did mention to say the first 4, yeah, it should be first 4, first 5. So hydrogen, helium, lithium, beryllium, boron do not attain octet. So this one has got a single electron, this one has got 2, this one has got 3, this one has got 4, that one has got 5 electrons. So in the outermost shell, hydrogen has got 1, helium has got 2 as it is. Lithium has got 1, since its electron configuration is the first energy level occupies a maximum of 2. So there will be a single one in this outermost shell since it's in group 1. Beryllium is in group 2, boron is in group 3. So it's easier for these to basically, if you look at a metal like lithium, it's very easy for it to lose an electron rather than gain the 7. So it's also very difficult for beryllium to gain all the way up to 6 electrons. And then it's also difficult for boron to gain 5 electrons. So instead, beryllium and boron will use what they have, since these are the ones that are performing covalent bonding. Hydrogen will use its single electron to make it 2. So boron and beryllium will not attain any octet. It will not. Of course, beryllium is going to stick to 2 electrons. Okay. So that's why they basically are restrictions. They don't attain octet. So beryllium has got 2 valence electrons. So that is going to be straightforward. It has got 2 valence electrons in that is coming from group 2. So go direct. We've got 2 chlorine atoms. So obviously, we can only have a maximum of 2 bonds in this case. We know why, because beryllium is only having 2 valence electrons. We cannot use more than what we have on the central atom. So this is a unique case. So we have chlorine on the 2 sides. Now you realize that you observe that chlorine is actually going to be stable in that it will have its 6 valence electrons like that, and then we know that it has donated 1 on each end. So that is beryllium chloride. So, and then we'll look at the other part, BH3 for boron. Boron has got 3 electrons in its outermost shell. 3 valence electrons, that is coming from group 3. So we have beryllium with how many hydrogens? There are 3 hydrogen atoms of beryllium there. So, sorry, not C, beryllium, boron, that is B. So it has got 3 as maximum electrons. So what do we expect for the shape? So we use 3. So all the 3 are going to be used to form bonds with hydrogen atoms. So we can just put them like that as trigonal. Okay, so hydrogen is something that is undecided. It's always known that it will only form a single bond. That's it. So all the electrons have been used up. These are the few restrictions below the octet. So we'll proceed and look at the advanced ones a bit. So sulfur dioxide is very interesting, as you'll see. So both sulfur and oxygen are in group 6. So we've got 6 valence electrons. So we know there's need of how many electrons? They'll need 2 each to make it 8. So for oxygen, we've got 2 oxygen atoms, so you'll need 4. 4 plus 6, 4 plus 2, 4 plus 2 gives us 6. 6 divided by 2 will give us 3 bonds required. Okay, so this is the formula we've been working with, but we'll see that it's not going to work here, in that I'm introducing a new aspect to you of formal charges. Okay, so sulfur is expected to form 3 bonds, right? Like that. So we can have 2 bonds on one side and then a single one like that. So how many electrons does that one need? That one needs 6 electrons together with a bond to make it 8, and then this other one will need just 2 together with the bonds. It is stable. The central atom has got 3 bonds around it, implying that it has got 6 electrons, so it needs 2. And you need to make sure that all these electrons we've looked at are equivalent to the number of valence electrons. So remember that we have got 6 for sulfur and then 6 by 2 for 2 oxygen atoms. So we have a total number of 18 electrons present. So in that oxygen, we've got 6. Lone pair, a bond has got 2. Sulfur has got 2. That bond, 2 bonds have got 4 electrons. The oxygen has got 4 lone pair. So if you get to add these, are they adding up to 18? So 6 plus 2 plus 2, that is 10, plus 8, that is 18. So that is correct. So somebody can come up with that as a Lewis structure. Okay. Now, we need to understand now the concept of formal charges. So, a formal charge. So, the way it is when it comes to Lewis structures, the best Lewis structure is the one which has got fewest charges. Okay. Fewest charges. And then the one that puts a negative charge on the most electrostatic or the most electronegative atoms is actually more stable. So it is not a good thing to have a positive charge on the central atom. Having a negative is better. That is according to formal charges. So how do you basically get to determine the formal charge? So a formal charge is given as the valence electrons of that atom subtract the number of bonds and also the number of lone pair electrons around it. So you subtract everything around it. That's the way I simplify it. Subtract everything around it. So in this case, sulfur has got 6 valence electrons. How many things are around it? So count a bond as a single. So 1, 2, 3. And then the lone pairs will be counted individually. So 3, 4, 5. So the difference is a positive 1. For oxygen, this oxygen on the right hand side, we have 1, 2, 3, 4, 5, 6. 6 minus 6, it has got 0. The one on the left, we can count 1, 2, 3, 4, 5, 6, plus a bond, 7. So it has got a negative. Those are the formal charges. Okay. Now, there's another suggestion to say sulfur can have 2 bonds instead. Okay. It can have 2 bonds instead on each side. 2, 2. Oxygen, oxygen, like that. Okay. And then the oxygen atom, we know that they're in need of how many electrons? Just 4 in this case. So we need to have 18 electrons used up. So we've used 4 on the oxygens, and then the 2 bonds on each end are having 4 electrons. So 4 plus 4 plus 4 plus 4, we have 16. So we are remaining with 2 electrons. So the excess ones will be on the central atom. So this is an exception to the octet. Sulfur is able to exceed octet. So due to that presence of that lone pair electrons, there is going to be bending there. So the actual structure bends like this with the 2 lone pair electrons there on the central atom. Now, I need to show the formal charges. So we said formal charges is the valence electrons minus everything around it. So I'll start with sulfur. Sulfur has got 1, 2, 3, 4, 5, 6 things around it. I'm counting lone pairs individually. We've got 2 lone pair electrons with 4 bonds around it. So 4 plus 2, 6. So 6 minus 6, 0. All the oxygen atoms have got 6 valence electrons. We'll count the things around them. We've got 1, 2, 3, 4 lone pair electrons plus 2 bonds, giving us 6. 6 minus 6, 0. On the right as well, 0. So here we've got 0 formal charges. So we said the base Lewis structure has got fewest charges and also puts a negative on the most electronegative atom. Okay. So that's why this one is actually does got fewest charges. There are no charges actually there. They are neutral. So this is the most stable structure of sulfur dioxide that is acceptable. And like that one, despite it having octet. So this is basically an exception to the octet. And of course, you've been introduced now to the aspect of determining the formal charges when it comes to Lewis structures. We'll look at SO3, a very interesting compound as well. How do we get to give this Lewis structure? SO3. So equally, we expect sulfur to exceed. Okay, we expect it to exceed octet. We have SO3. Let's try to see. Sulfur has got 6. Oxygen 6. They all have 6 in the outermost shell. Now I would have to multiply by 3 because we've got 3 oxygen atoms. So how many do they need first of all? How many electrons are they in need of? Sulfur is in need of 2. Each oxygen atom is in need of 2. Now we've got 3, so it will need 6 in total. How many do we have in total? So 2 plus 6 gives us 8. How many bonds do we need? 2 plus 6, 8 divided by 2. We need a total number of 4 bonds. Now, this is where now the formula doesn't work. So formula doesn't work. So you've seen that even from the previous example, it didn't work. Okay. So when it comes to the exceptions to octet, that formula doesn't work. We'll see later that even when it comes to odd numbered valence electrons, it doesn't work when it comes to the central atom. So therefore, in this case, we'll try to use the valence electrons we have. So the valence electrons we have is, for oxygen, we have got 3 by 6. So we have 18 plus 6, which gives us 24 valence electrons. So we'd have to distribute these 24 valence electrons in a way that everything is going to be stable with fewest charges. So we have S with 3 oxygen atoms around it. Okay, so let's try to see what we can do to distribute the bonds around. Okay, so the simplest way, as we saw from the previous example, is we saw sulfur forming 2 bonds with each oxygen atom. So that is preferred when it comes to sulfur. So we can do the same. We'll put 2 bonds on each side. So we know that each bond carries 2 electrons. So we have got 4 there, 4 electrons, 4 electrons. 4 by 3, we've used up 12 electrons already. How many electrons are remaining? We're remaining with 12 more. So we can put on the oxygen atoms to balance them up. So the fact that they've got 2 bonds on their side implies they have 4 bonds. They've got 4 electrons, so they just need 4 more. So we'll put 4, and then we'll put 4, and then we'll put 4. So 4 by 4 by 4, if you get to count as well, you also get 12. So all the electrons have been used up. So we are not going to have any presence of lone pair electrons on the central atom. So it wasn't necessary to leave that space. So that's why if you look at the actual Lewis structure, it balances up this way. Okay, so there's no need of leaving that space, knowing that they are repeating each other. Okay, so you have the oxygen atoms like that. Of course, make sure you show the valence electrons. And of course, in conclusion to this video, we can just look at the one more structure, which is NO3 minus, introducing us to the aspect of the effect of a charge on an atom when it comes to coming up with a Lewis structure. How do you get to approach that? So equally, here we are going to use a formula. We understand that nitrogen and oxygen cannot exceed the octet. So nitrogen has got 5 valence electrons, oxygen has got 6 valence electrons. So what is the shortage? Nitrogen needs 3. Oxygen needs, that is like, it needs 2. There are 3, it will need how many? It will need 6. And then of course, whenever I've got a negative charge, it implied there was gain of an electron. So it is supposed to add 1. So for a negative charge, add the equivalent number to the number of valence electrons. Sorry, it's not supposed to appear on the... This is now where it becomes tricky. So what I'm doing here is, I'm trying to determine what is required. So the way it is we're supposed to consider a negative as an available electron. So I'll count it as among the available electrons. So we have 5 on the nitrogen. For each oxygen atom, we have a presence of 6 by 3. Now, the negative is supposed to be added as an available electron. So now, looking at what is required, we have got 3 plus 6. Okay. Now, that was what was supposed to be required. Now, the fact that there was gain of an electron, it's supposed to reduce the number of required electrons. I think that's a point that I needed to make there. So A negative implies there's gain of an electron, so it reduces on the number of required electrons. So subtract it from the required number of electrons. So 3 plus 6 is 9 minus 1 gives us 8. Okay, that was a necessary of that electron. So if it was a positive charge, we were going to add it on the required electrons because it would imply there was loss of an electron. Okay, so we need 8 electrons. Divided by 2, it will be covered by how many bonds? 4 bonds. So a central atom, in this case, it is nitrogen. Nitrogen is less electronegative as compared to oxygen in that it is in group 5, oxygen is in group 6. Okay, I believe we already know that electronegativity increases from left to right if you look at the periodic table. So therefore, we have N as our nitrogen, and then we've got oxygen atoms around it. How many are there? There are 3. Okay. So 3 oxygen atoms. How many bonds are we having? We are having 4 bonds. So one is supposed to have 2. So you can put them anywhere where you want. Okay. And then try to cover up now for the lone pair electrons. So the one which is having 4 bonds, which is having 2 bonds around it for the oxygen atom, it has got 4 electrons around, so it just needs 4 more. And then the one having a single bond, it has got 2, so it needs 6 electrons around it. So those are 2, they'll need 6 electrons around them. This is the way the Lewis structure is going to end. Okay. So we'll put it in brackets, put a negative around it, showing that there was gain of an electron, since the structure itself shows the negative there. So this basically introduces us to what we call resonance structures. So you can draw a resonance structure by drawing another diagram of the same nature, but showing the double bond on a different oxygen. Remember, there is no rule there, so it can be on any oxygen. Okay. So that introduces us now to what we are calling now the resonance structures. So we'll talk about them more. So you put was to show. So we'll talk about resonance structures in the other video. Make sure you watch it. We're going to talk about the exceptions to the octet rule. So we'll look at examples of cases where it is less than octet, and then also cases where we get to exceed the octet. Okay, so according to the octet rule, the valence shell must have 8 valence electrons for it to attain stability. Okay, so one thing that I would want you to understand is the first 5 elements of the periodic table don't follow that rule. That is, okay, so hydrogen, we know that the first shell of any element must only have 2 electrons, okay, because it only has the s orbital, so only 2 electrons. So hydrogen only has 2, it gets to get 2 electrons only. That applies to helium, which already has got 2 electrons. Lithium, which has got 3 electrons, since it's a third element, just loses the outermost electron to remain with a 2. Okay, and then beryllium, which we are going to talk about together with boron. So beryllium is number 4, boron is number 5. So we know that beryllium is coming from group 2, and then boron is coming from group 3. So how are they exceptions to the octet rule? So we basically understand that as you look at barium chloride there, we know that chlorine desires to form a single bond. So in this case, from the Lewis theory, we already have a foundation to say the valence electrons are very necessary when it comes to forming bonds. So since beryllium, which is going to be the central atom because we put the least electronegative atom on this to be the central atom, beryllium is going to be the central atom in this case. So we have beryllium there joining to 2 chlorine atoms. So we understand that the central atom is supposed to contribute an electron to each bond. So in this case, in the 2 bonds, there is a single electron contributed by beryllium. So all the valence electrons of beryllium are used up. Since it's from group 2, group 2 elements have got 2 electrons in their outermost shell. So it cannot form any more bonds there. And then all the valence electrons are used up. It has got no lone pair electrons. Okay? Of course, we do understand that there's supposed to be 6 electrons on the chlorine atoms. So that implies that out of its 7 electrons, 1 has been used to form the bond with beryllium by each chlorine atom. Okay, so that's an exception to the octet rule. Why? Because beryllium, which is the central atom, is only surrounded by 4 electrons, 2 from each bond. Okay, now talking about the other one, which is boron. Boron also is only capable of forming up to 3 bonds because it has got 3 valence electrons. It is coming from group 3. So write it. So boron forms trigonal planar, as we get to look up about molecular geometry to understand what that means. So we have fluorine joining. So we can even have hydrogen, whatsoever can join there. It's going to form a maximum of 3 bonds. Why? Because it has got 3 electrons in its outermost shell. So the 3 electrons will be used to form a maximum of 3 bonds. So notice that all its electrons have been used up. It has got no lone pair electrons. So this is basically an exception to the octet because it is only having 3 bonds. 3 bonds, each bond has 2 electrons. So it is only having 6 electrons, which is below the octet. So it's an exception to the octet. Okay. We can now look at an example with an odd number of electrons. So we're now looking at the nitrogen dioxide. How is it going to be? So determine first of all the number of valence electrons. In that case, so we understand nitrogen is coming from group 5. Oxygen is coming from group what? Group 6. So 6 times 2, that is 12, plus 5, that is 17. So that's an odd number of valence electrons. So how do we get to distribute those ones? So we understand that in this case, nitrogen is less electronegative as compared to oxygen. So it's going to be the central atom. So how do you basically get to balance up the electrons? Okay. So we understand that oxygen is supposed to be balanced up. Okay, we're supposed to balance up the oxygen. So the way this one comes out is it basically gets to form a single bond with one oxygen atom and then a double bond with the other oxygen atom, like that. So if you check at that point, how many electrons have been used up? So each bond uses 2 electrons, so you now have 6 valence electrons used out of the 17. So if you remove 6, you remain with 11. So how are the 11 going to be distributed? So we need to prioritize the oxygen. So this oxygen with a single bond will need 6 more electrons to make it 8. Then the one with a double bond will need 4 more electrons. So we've used 6 plus the 4, making it how many? So that makes it to be 10. 10 from 11 remain with a single electron. So that single electron will just be put on the central atom. Okay. So that is basically what we have in this case. So that is an exception to the octet. So we can try to count the number of electrons that we've used up if we're adding up. So for the bonds, we've got 3 bonds, 6 electrons, that is. On the oxygen atom, there are 6 lone pairs on the left. And then on the right, there are 4, plus the electron on the center. So that is 17 valence electrons. Okay. We're now talking about the ones that get to exceed the octet. That is, they get to occupy or accommodate more than 8 electrons in the outermost shell. So we understand that these are coming from period 3. So in period 3, elements such as silicon, phosphorus, sulfur, chlorine have got an ability to exceed the octet. Why? We understand that as we get to talk about electronic configuration, that is, we'll look at the third period. In the third period, that's where we have an existence of 3s2. We've got 3p. We've got 3d. So what are we trying to say here? So we're trying to identify the fact that if you check or look at the Fed period, so there's an ability of having up to 18 electrons. That is 2 plus 6 plus 10, that is 18. So that's why these are able to exceed what? The octet. Okay, so look at these examples that we have. So phosphorus, we know phosphorus is coming from group what? Phosphorus is coming from group 5. So write it. Chlorine is coming from group what? Chlorine is coming from group 7. So we understand that in such cases where you have up to 5 chlorine atoms and then you've got 5 valence electrons, there's no need of you to think there. You can just go direct actually. So you expect the central atom to be phosphorus in this case because it is actually less electronegative as compared to chlorine atom. So now all these chlorine atoms will get a single bond. So count 1, 2, 3, 4, 5. So all the 5 valence electrons have been shared by the chlorine atoms that we have in this case. So don't forget that all the chlorine atoms are going to have 6 lone pair electrons to make sure that they are balanced. Okay, so you can finish it up there. So the main idea there, the main observation we are trying to make is we are seeing phosphorus forming up to 5 bonds. And we know that each bond comes with 2 electrons. So making it actually to have more than what? To have more than 8. So it has got 10 around it. So that is an exception to the octet. Okay. We can talk about the next example, which is iodine, Cl5 there. Okay. How do we expect it to come out? So equally, we know that if you check our periodic table, where is iodine coming from? I think iodine should be coming from group 7. If I check my periodic table, iodine is coming from group 7. So it has got 7 valence electrons. So how is it going to be? So iodine will be our central atom, of course. And then we've got 5 chlorine atoms. So chlorine atoms will form a single bond each. So 5, that is. Now out of 5, we expect that there will be an excess of how many electrons? We remain with 2 electrons to make it 7. So the 5 bonds plus the 2 electrons will make it 7. Okay. So I'll count the bonds now. So remaining with 3. So all these are going to be chlorine atoms joined to the iodine. So chlorine there and also chlorine there. So this is basically the way we expect iodine to come out and form a Lewis structure. Of course, each chlorine atom would have 6 lone pair electrons around it. Okay, so if you count the number of bonds, we've got 5 bonds plus the 2 lone pair electrons, making it 10. So it has exceeded the octet. Okay, that is an exception to the octet rule. So when you talk about SF6, we'll basically observe that we know sulfur is coming from group 6. So it has got 6 valence electrons. So they are all going to be shared up by the 6 fluorine atoms we have. Excuse me. So from there, we expect that there will be no lone pair electrons. That's what we expect in this case. So I have something like that. So all those will be fluorine atoms. So of course we expect them to have 6 lone pair electrons around them. So there will be no lone pairs on the central atom. All its 6 valence electrons have been used up. So each fluorine will have 6 lone pair electrons. So 6 bonds implies it has got 12 electrons around it. So it has exceeded the octet. Okay. So in each case where for you to balance up the bonds, you have to exceed 8. So that is possible whenever you get to look at the elements coming from the Fed period and beyond. Okay. So we've talked about examples like silicon, phosphorus, sulfur, chlorine going down. All those have got an ability to exceed the octet. So hopefully you now understand the exceptions to the octet rule. We're just going to look at how we get to calculate the formal charge using this compound. So at this point, we already understand that the formal charge is very important when it comes to choosing the lowest energy Lewis structure and the most stable Lewis structures in cases where we've got more than two structures available. Okay, because we understand that the one with lowest energy is the one with fewer or lower formal charges, and it's actually more stable in existence. Okay, so how basically do we get to calculate the formal charge? So the formal charge formula is basically given as the number of valence electrons minus the lone pair electrons minus the bonds. Okay, so that's the full formula. Now, the simplest way of you remembering it is this. Formal charge is equal to valence electrons minus anything around it. That's the way I take it myself. It's very simple that way. Okay, so we'll look at it in this way. Looking at the formula that we have on the bottom, it is the number of valence electrons. So we'll start first of all by the sulfur, or go by the oxygen on the bottom. This oxygen there. So how many valence electrons does oxygen have? So oxygen basically has got valence electron that matches up with its group. So all elements are like that on the periodic table. So we have 6. Now, how many lone pair electrons? We have 4 lone pair electrons. These electrons that are not part of a bond formation. So we have 4. And then how many bonds? There are 2 bonds. So in such a case, we realize that the formal charge of our oxygen there is expected to be what? Is expected to be a 0. Okay, that's the way you get to look at it. Now, instead of doing that, what you can basically do is look at the number of valence electrons and then just count everything around it. So count it as individually. So 1, 2, 3, 4, 5, 6. It will still be 6, right? So it will still be a formal charge of a 0. So that will apply to everything else. So we know that all these have got 6 valence electrons. So we'll just be subtracting how many things are around it. Starting with the oxygen on top. So it has got 4 lone pair electrons plus 2 bonds. So that makes it 6. 6 minus 6, 0. The one on the right, it has got 6 lone pair electrons with a single bond. So that makes it 7. 6 minus 7 is a negative 1. And then the one on the right, we've got 6 minus. So we've got 6 lone pair electrons plus a bond. So that also makes it negative 1. And then the sulfur. The sulfur itself, it has got how many bonds around it? 1, 2. So it goes 2 double bonds. That makes it 4 plus 2, 6. 6 minus 6 is 0, since it's also from group 6. So far what we are seeing is the ones in the sides are negative 1s. The ones on opposite, so we've 0, negative, negative, and a 0 on the sulfur. So it's not necessary for you to show the charge when it's basically all zeros. Okay, so therefore, from our calculations, the net charge of the entire compound is going to be the additions of all the signs. So therefore, we'll put it in brackets. Let me draw brackets better. Okay, so we have got 2 negatives, so to give us a minus 2. So 2 minus is the net charge of the entire compound. So that's why the formula is basically written to be S or for 2 minus. Okay, so that's how we basically get to determine the formal charge in the simplest way possible. Okay, so in cases where you're having some challenges when it comes to understanding why sulfur exceeds the octet, you can watch a video about that. So we'll begin looking at resonance structures. So resonance structures basically helps us to draw the same Lewis structure in different ways. So we'll look at it using these 2 examples. Okay, so I hope you've watched the video where I explained how to draw the Lewis structure using 2 steps. Okay, if you've not, check it out. So NO3 minus there. How are you going to handle this? So basically we understand that nitrogen is coming from group 5, oxygen is equally coming from group 6. Okay? I want you to understand that the negative sign on any compound in case that there was gain of electrons. Okay? So the method that I basically use when I'm coming up with a Lewis structure when it comes to elements in pH 2 and above, that is, sorry, pH 2 and 1. So we are going to determine the number of required electrons observing the octet rule. We know that octet rule observes a need of 8 valence electrons for stability. So nitrogen, to make it 8, since it has got 5, it will need 3. Okay? And then we expect that for oxygen, it needs how many? It needs 2. Now, since there are 3 oxygen atoms, it will be 3 by 2, giving us what? 6. Now, the negative sign indicates that we had gained an electron. So, the number of required electrons will be reduced by 1. So, how many electrons will be required now? 6 plus 3, which is the actual number of required electrons, gives us 9, minus the electron that was gained. It gives us 8 required electrons. So these 8 are supposed to be divided by a 2. A 2 represents a bond. So it will give us 4 bonds required. So we already know that the central atom in this case expected is to be nitrogen, since it's less electronegative. So we'll put nitrogen as our central atom. And then we expect to form how many bonds? We're expected to form 4 bonds. Okay, so I can remove the calculations there so that we have enough space. So there we have nitrogen forming how many bonds? Forming 4 bonds. And that's got 3 oxygen atoms. So how is the sharing going to be? How is the sharing going to be done there? So we expect that 1 oxygen atom is supposed to get 2. So I can start with this one. You can have 2. One will have 1. Also another one, 1. So these are the oxygen atoms. So I'll put the lone pair electrons. How many are they going to be? So put depending on the number of bonds. So for the oxygen atom with a single bond, they will need 6 electrons around them, like that. For the oxygen atom with 2 bonds, it will only need 4. So that one needs 6 on top. Okay. So now notice that somebody else can draw it in another way. How can they draw it? They can decide to draw the same structure by moving the double bond to the other side, like that. Then somebody else may also decide to put them on top. So I can just remove that structure for now. So I can put the double bond on top and then the single bonds on the bottom. So this is what we're calling now the resonance structures. You being able to do that is resonance. Okay? So now, there are some cases where they'll ask you to show how the electrons are basically moving. Of course, there's need for you to even to put these signs in between the structures. Okay, when you're drawing the resonance structures. So how is it going to be? So we understand that the double bond basically, the double bond has got 2 electrons. So this will go back to the oxygen atom. So that implies that in the next structure, we expect that there will be how many electrons? There will be 6 electrons because that double bond has moved back to its oxygen atom. And if that happens, we expect that a lone pair from this will come back here to form what? A bond, which is this bond that has been formed there. And then again, for us to go to the top part, we expect that this double bond is supposed to be broken by a movement of lone pair electrons. Of course, where it has got 2 bonds, it just have like 4 lone pair electrons. That one has got 6 at this point. So again, in the next structure, for us to have a formation of a double bond there, we've seen that there should be a movement of lone pair electrons to form a double bond with a nitrogen atom. Okay, so in the last structure, the ones on the bottom will have 6 lone pair electrons, and then the one on top will just have 4. So this is the basic idea when we are talking about resonance structures. This is how you get to show them. Okay, so you're just trying to show that you're not restricted to you having a double bond on a single oxygen atom, but it can also be on another part. Okay, so these are the three possible ways of drawing NO3 minus, and this is exactly what we call resonance structures. Let's look at another example. Where we have CO3 2 minus. So how do we basically get to look at that? So here we know that carbon is coming from group 4, oxygen is still coming from group 6. So how many electrons are required? So for carbon we need 4. For oxygen we need, since that goes 6, we need 2 for each. So 2 by 3 will give us what? 6. Now the 2 minus implies we had gained 2 electrons. So the number of required electrons will reduce by 2. So 4 plus 6 gives us 10. 10 minus 2 gives us what? Gives us 8. So we need 8 valence electrons. So this will be replaced by the number of what? Bonds. So we can divide by 2. So we expect to have formation of 4 bonds to balance up the valence electrons. Okay. So we now know the number of bonds that we expect to form. 4 bonds as well. So carbon will be our central atom. We'll form the bonds. So first to balance up, this one I'll start with a double bond on top like that. And then for the other one, I can move it to the left. And then for the last one, it can be on the right. Okay, like that. So I believe you now know how to draw the resonance structures. So you can pause the video and finish it up. Okay, so the lone pair electrons, how do we expect the lone pair electrons to be? So where there's a double bond, it should just be 4 to make it 8. Where there's a single bond, there should be 6 electrons present. Like that. Okay, you have 4. There will have 4. Elsewhere we'll have 6. Like that. Even on the last one. So we need to show now. So we have these lines that I told you need to show that it is able to move from that one and become and exist in another form. And then of course, in cases where there's need to show the movement of electrons, you need to understand all that. So what is basically happening from the first structure to the second structure? So you're observing that there was a double bond. So a double bond is supposed to break. So we'll show a movement of, we know that a double bond has got 2 electrons. So the 2 electrons is what is basically making the electrons to become 6 there. Okay. Now from there, we also have the formation of a bond. So out of these 6 lone pair electrons, 2 of them will form a double bond there with the central atom. That's why you're remaining with 4 now on the next diagram. The same concept to apply. A double bond will break there. And then there will be need to form a double bond there. So out of the 6, 1 will form a double bond. 2 of them will form a double bond, remaining with 4 now on the last diagram. So this is basically how you get to present the resonance structures under chemical bonding. It's not something that is complicated. It's very, very simple. So understand that the compound is able to exist by having a double bond with different oxygen atoms. So this is just an example. There are many resonance structures that you'll be able to meet as you get to study your chemistry. So hopefully you now have got an idea on how you get to approach resonance structures. We're just going to review the concepts that are behind the bond strength, which leads to bond enthalpy, and then also a bond length. Okay, so if you look at carbon with a single bond, and then you look at carbon with a double bond, and then you look at carbon with a triple bond. So which one do you think is stronger when you compare these three? Which one is stronger? So obviously we expect that in terms of bond strength, the one that is stronger is the triple bond, right? So that bond strength can now give birth to what we are calling the bond enthalpy. So bond enthalpy is basically the amount of energy that is required to break a bond. Okay, that is what we call bond enthalpy. So triple bond has got the higher bond enthalpy as compared to the double and a single bond. Of course, this also tells us that there's a different concept. Consider a case where you have oxygen to oxygen enthalpy. So that is also different from what we have right now. Of course, when you're talking about oxygen, we can even put a double bond there. Okay. So the bond enthalpy of that bond is 495 kilojoules per mole. And then the bond enthalpy of the carbon to carbon, that is a single bond, the value is 348. So you can see that I think it was unfair for me to compare with single bond of double of carbon and then okay, let me compare against a double bond of oxygen, of carbon dioxide, that is. So if you look at the double bond, it's 614 kilojoules. So now that's fair enough to compare the two since they are all double bonds. So even double bonds have got different amounts of energy, but the bond enthalpy of the amount of energy required is different. So I can say in this case that carbon to carbon is stronger as compared to oxygen. Okay, that's it about bond enthalpy. Now, in terms of length, which one do you think is longer? Is it a single bond, a double bond, or a triple bond? Which one do you think is longer? So if you look at that, the actual length of these bonds are as follows. This is 1.54 angstrom. 1.54, not 1.5. So 1.54 in angstrom. Then of course that is 1.34, 1.20. So all these are in angstrom. So which one is longer? So we can now see that the single bond is actually longer. The double bond is not as long, and then the triple bond is the lowest. Okay, so shorter. So we've observed now that the bond strength, which gives birth to a bond enthalpy, which is the amount of energy required to break a bond, is actually higher in multiple bonds as compared to a single bond. And then the bond length is longer in cases where they're weaker, or in a single bond is longer as compared to double and the triple bonds. Alright, so in this video, we're just going to talk about the VSEPR theory. What exactly is the VSEPR theory? So the VSEPR theory, of course, the letters stand for valence shell electron pair repulsion theory. Okay, so it's a very simple concept, which of course is used to predict the molecular geometry based on the number of the valence shell electron bond pairs among the atoms in a molecule. So what this theory tells us is electron pairs will arrange themselves to minimize repulsion from one another. So electron pairs, so I'll just write that, electron pairs tend to arrange themselves to minimize what? Tend to arrange in a way to minimize repulsions. That's exactly what this theory states. So this tells us that in a case where you have, for example, carbon dioxide, so assuming these bonds are like this at forming. So the closeness there is a repulsion. So they are going to arrange themselves in a way that they are the repulsions are minimized. So that gives birth to such an arrangement. Okay, that's what this theory tells us. So in this case, there are minimal repulsions as compared to the case that I drew. Now let's consider water as well. Now if you look at water, so H2O, this is something, let's assume we have something like this. I'm even beginning to forget these things. So H2O. So you find that this oxygen has got lone pair electrons there. So now these electron pairs, you remember in a bond there are two electrons. So there is also repulsion between the lone pair electrons and the bond. So there's need that the water molecule arrange itself in a way that it has minimized the repulsions. Of course, in this case, we can clearly see that there are minimal repulsions between the bonds. Okay, but still, it has to be balanced. So there are still more repulsions with the lone pairs there. So this leads to a case where we have such. So this is now balanced. So there are minimal repulsions there. So repulsions are minimized between the bonds and the lone pairs, as well as between the bonds and between the lone pairs. So that's what this theory basically helps us to do. So it's the one that is going to be helping us to predict and visualize the molecular structures. Of course, we'll look at things like linear. For example, I've already given an example of what? Of carbon dioxide, that's linear. Of course, we'll look at things like trigonoplanar, tetrahedral, trigonopyramidal, trigonobipyramidal, and so many, T-shaped, octohedral, square pyramidal. There are a lot of these. So I'll take you through the angles and also how you basically get to name the shapes. Okay, so having introduced you to the VESPA theory, I'm just going to give you a summary using the help of this diagram, a summary of the electron, the molecular geometries that you have to know. Of course, more in details, there are a few videos you have to watch below. Just one on this, and of course one on the molecular orbital theory and also the valence bond theory. Okay, so now, what exactly is the difference between electron and molecular geometries? So electron involves you showing the lone pair of electrons on the central atom. Of course, we understand that the lone pair is actually a part of, for example, if you look at oxygen in water, so this one has got so there's a nitrogen there. This one has got two pairs of lone pair electrons. Two lone pair electrons, four lone pair electrons actually. So actually this is a lone pair. It's a pair of two electrons that are not taking part in a bond formation. So now, in a case where you are naming this water molecule, where you even include these in the structure formed, we call this now electron geometry. Now, in case of molecular geometry, you ignore the lone pair electrons on the central atom. So that is, you only focus on what is on the bonds. So in such a case, you end up with a shape like bent. Now we'll see what exactly it can be called when you've got two lone pair electrons like that. I think it forms a shape more like what shape forms? It's more like anyway, tetrahedral or something like that. It's the closest so far. Okay, but let's get back to the diagram. So now we understand the difference between molecular and also electron geometry. Now, we'll start with two bonds. Okay, we'll start with two bonds. So if you look at two bonds, a very good example we have is linear. So I already gave you an example of a linear compound. That is carbon dioxide, right? Where there's something like that. So there are clearly no lone pair electrons on a central atom. So That's why the electron geometry and the molecular geometry are basically one and the same. So electron geometry and molecular geometry, they are the same because there is no pair of lone pairs of electrons. So linear, it's because it's a line. Linear means straight. So the angle between the two bonds or the two sides is basically 180 degrees. We understand that in a straight line, right? So we can move to a case where you've got three connections. So when you have three connections, the two possible results are it's either you have three bonds or you have two bonds and a lone pair of electrons. Okay, so a very good example we can have for three that is think of what? Boron tetrafluoride. Yeah, is it boron tetrafluoride? No. Yeah, tetra. Yeah, think of BF3. Let me not confuse myself. So, yeah, something like that. So that is already something that is going to form three connections like that. So boron will be connected to three fluorine atoms like this. Of course, it's supposed to appear there. So that is trigonal planar. Okay. Now, giving you an example of, do you have any example you can give in terms of, yeah, anyway, we can end there. So this is called trigonal planar. Whenever you've got three bonds, it's called trigonal planar. So now, if you look at this, where am I? Okay, my mouse is not appearing. Okay, so if you look at this part, there is no lone pair electron on the central atom, right? So that's why it's the same with the molecular geometry. Now, if you check the other side, a case where you've got a lone pair. So in terms of our electron geometry, it is called trigonal planar. Now, as you proceed to the molecular geometry, this is what I was talking about even under water. Okay, so we saw the same. Okay, you look at this, it becomes bent after ignoring the. So molecular geometry requires you to ignore the lone pair electrons on the central atom. We can move on to four connections. So four connections, when you have four connections, all the four are present, it's basically called tetrahedral. So two linear, three trigonal. Okay. The only changes, of course, if there is a lone pair present, the molecular geometry becomes different. Okay. Now let's look at what we have in this case. So what good example can we have for a tetrahedral? What good example can we have? Okay, am I able to think of anything? So you can think of methane, for example, carbon connected to four hydrogen atoms. So that is clearly tetrahedral. Okay, that's an example you can have. So when you've got four connections like that, it's tetrahedral. Now considering a case where you may have one of them being a lone pair of electrons, when you got the molecular geometry, it becomes, you disregard it. So it's a pyramid that is formed. Now the fact that it's three, it's called trigonal pyramidal. Okay. So trigonal pyramidal. So of course, even as you are ignoring the lone pair electron, you of course understand it has got an effect on what? It has got an effect in terms of repairing the bonds. So that's why they are bent downwards. And of course, this theory tells us that a lone pair has got actually repels more compared to the bonds themselves. Okay. All right. So take note of that. Now I gave you an example. This one is an example of water. I gave you an example of water. What did I say? I said if you look at water, which is H2O, it is something that is like this. So I said when you consider the lone pair electrons, it actually forms four things. So it's tetrahedral as an electron geometry. Now, as a molecular geometry, they are supposed to be ignored. So what remains is a bent shape. And that's exactly what we're able to see there. It's now bent after removing the two lone pairs. Now we can move to, of course, I didn't even focus. There are actually examples, and I was struggling with examples. Examples were on the bottom here. The Lilium chloride is an example of linear. BH3 is an example of trigonal planar. This is, of course, an example of trigonal planar in terms of electron geometry. If you remove the lone pair, it becomes bent. Of course, water has also been given for the last one. Now, take note of the angles as well. So trigonal planar, for the linear, sorry, it's 180. For linear, it's 180. Then for trigonal planar, the angle is 120 degrees. And then for tetrahedral, 109.5. Okay, now just a few things to take note of, things that are not covered from the previous example. So we just went as far as trigonal pyramid, where you have a lone pair electron lost. When you have a lone pair, we've got 3 bonds and then a lone pair. It's trigonal pyramidal in terms of molecular geometry. So this one is not talking about electron geometry, just molecular geometry. Now there's a few things that we didn't talk about. So what about a case where you've got 6 connections and then 2 of them are lone pair electrons? So it gives us what we are calling now a square planar. Okay, they're in the same plane, but it's a square. And then tetrahedral, of course, has already been talked about, 4 connections. Trigonal bipyramidal is a case where you've got 5 connections. Trigonal bipyramidal. Octohedral, you've got how many? So you have 6 connections. So you need to review all these to have an understanding of what they are. Okay, it's very easy for you to come up with a molecular geometry and also the electron geometry. So I believe after watching this video, you're able to name the electron geometry and the molecular geometry of the respective Lewis structures that you earlier learned in this series on how to come up with them. So how exactly do you get to name them? I'm sure you now know that from this video.